Welcome to tonight's journey into the hidden world. Close your eyes and let your breathing stabilize. The day has ended across your specific time zone. It is time to leave the surface world behind. Your mind requires a quiet place for deep rest. We offer you a safe passage to the depths. Tonight we explore the ancient Mediterranean vent systems. These are the oldest hydrothermal networks on planet Earth. Rest your physical body on your comfortable sleeping bed. Allow your thoughts to detach from daily waking routines. The ocean provides a perfect sanctuary for natural sleep. Water absorbs all the chaotic noise of human civilization. Below the waves lies a realm of absolute tranquility. You are secure in this virtual deep submersible vessel. Our cabin maintains a perfectly comfortable temperature for you. The acoustic insulation blocks out all exterior ocean sounds. Focus only on the steady rhythm of my voice. Each spoken word serves as a stepping stone downward. Your muscles can finally release their long-stored tension. Take a slow breath of the filtered cabin air. Exhale and prepare for an extraordinary geological scientific expedition. We begin our scientific expedition in the Mediterranean Sea. This expansive body of water holds countless ancient secrets. Human history unfolded along these sunlit coastal European shores. Yet few people know about the alien landscape below. Our exact navigational coordinates read 39 degrees north. The longitude is 14 degrees and 30 minutes east. This specific location places us directly in the Tyrrhenian Sea. The Italian peninsula lies to the east of our position. The large island of Sardinia rests far to our west. We float high above a submerged active volcanic arc system. Oceanographer Michael Mahoney extensively mapped this very specific region. His detailed sonar surveys revealed a complex underwater topography. The surface waters here reflect a brilliant azure blue. Gentle ocean swells rock our vessel before the initial descent. The Mediterranean is a deep remnant of the Tessis Ocean. It originally formed millions of years before modern human evolution. This semi-enclosed basin features truly unique hydrological circulation patterns. High surface evaporation rates create incredibly dense and salty water. This heavy liquid naturally sinks toward the dark ocean floor. It creates a remarkably uniform deep water chemical environment. The geology far beneath us remains incredibly active today. We are positioned directly above a major tectonic plate boundary. The massive African continental plate pushes northward right here. It collides directly with the stationary Eurasian continental plate. The African plate advances at a few millimeters annually. This slow motion shapes the entire Mediterranean geological framework. This tectonic collision creates a classic subduction zone environment. The heavier African crust slides beneath the European landmass. Friction from this movement generates immense subterranean thermal heat. Solid rock melts into liquid magma deep within the Earth. This superheated molten material rises toward the seafloor crust. It fuels the hydrothermal vent systems we will study soon. The Aeolian volcanic arc dominates this hidden underwater region. Several massive seamounts pierce the flat abyssal plain below. We target the Marsilii seamount for tonight's primary observation. It is the largest underwater volcano in all of Europe. The geological structure stretches 70 kilometers in total length. Its width spans roughly 30 kilometers across the ocean bottom. The tectonic forces here have operated continuously for millennia. They shape a rugged landscape of sharp basaltic rock ridges. Deep fractures in the crust allow cold seawater to penetrate. This creates the complex plumbing system for hydrothermal fluid activity. Earthquakes frequently originate from this deep crustal friction zone. Seismometers placed on the seafloor record these distant tectonic tremors. The low vibrations travel through the rock as acoustic waves. The extreme age of these vents sets them completely apart. Some structures have vented hot fluids for many thousands of years. They easily outlast the transient vents of mid-ocean ridges. This remarkable longevity supports highly specialized biological communities nearby. Our submersible begins its vertical transit through the water column. The digital altimeter tracks our increasing distance from the surface. We smoothly pass the 500-meter ocean depth mark. The twilight zone fades into complete and absolute visual obscurity. We bypassed the vibrant mesopelagic zone hours ago during descent. That region hosts the largest daily migration of marine life. Millions of small creatures travel upward to feed every night. They return to the protective shadows before the sun rises. We are now far below their normal vertical biological range. We reach 1,000 meters below the global sea level. This depth marks the beginning of the dark bathypelagic zone. The water temperature here stabilizes at exactly 14 degrees Celsius. This is unusually warm for deep ocean environments across Earth. Most abyssal waters hover near the freezing point globally. The enclosed nature of the Mediterranean basin traps this heat. Our descent continues steadily past 2,000 meters deep. The ambient light level reaches absolute mathematical zero down here. Solar photons cannot penetrate this massive volume of seawater. The local ecosystem relies entirely on subterranean chemical energy sources. We slowly approach the 3,000-meter depth threshold now. The rocky summit of the Marseille seamount comes into range. Sonar instruments ping the jagged volcanic peaks just below us. Our mechanical thrusters adjust to maintain a perfectly steady hover. We are suspended in an endless void of liquid space. The exterior depth gauge reads exactly 3,000 meters down. This extreme isolation provides a profound sense of psychological peace. No violent surface storms can ever affect this benthic sanctuary. The massive water column acts as a thick protective shield. The physical conditions here are incredibly hostile to human biology. Atmospheric pressure increases by 1 unit every 10 meters down. At this extreme depth the pressure is 300 atmospheres. This equals 300 times the normal atmospheric surface pressure. Every square inch of our hull bears an enormous weight. Over 4,000 pounds press on each square inch constantly. Our titanium sphere easily withstands this crushing physical ocean force. The brilliant engineering provides you with absolute mechanical structural safety. Unprotected organic matter would compress almost instantly down here. A normal styrofoam cup would shrink to a tiny fraction. Its cellular air pockets would completely collapse under the strain. Yet the local endemic fauna has adapted to this weight. Their cellular membranes contain highly specialized pressure-resistant structural proteins. Chemical piezolites in their tissues prevent vital proteins from deforming. High pressure also alters the fundamental chemistry of the ocean. Gases dissolve much more easily in this highly compressed liquid. Oxygen and carbon dioxide remain securely trapped in the solution. This unique chemical state supports the bizarre vent biology ahead. Water itself compresses slightly under these extreme physical depth conditions. This increases the overall density of the surrounding fluid medium. The heavy water moves with a sluggish and physical grace. Ocean currents at this depth flow at a very glacial pace. They transport dissolved minerals across the vast flat abyssal plain. The sheer invisible weight of the ocean induces deep relaxation. Imagine that pressure absorbing the heavy weight of your worries. It crushes daily anxiety into microscopic and harmless little fragments. The darkness outside our viewport is absolute and totally infinite. It is a pure and total absence of all visible light. Surface nights still feature pale moonlight and scattered distant starlight. Here the blackness possesses a tangible and heavy physical quality. Our external floodlights remain switched off for the time being. We allow our human eyes to adjust to the void. This visual deprivation calms the optic nerve completely and naturally. Your brain stops processing endless streams of incoming visual data. The darkness wraps around the submersible like a thick blanket. It is a comforting and protective layer of ancient water. Bioluminescence occasionally sparks in the distance like tiny falling stars. Microscopic organisms emit chemical light to communicate or hunt prey. These brief sudden flashes only emphasize the surrounding endless dark. The ocean water absorbs the blue spectrum of light last. Now even the deepest blue has vanished completely away forever. Only a profound and monochromatic obsidian environment remains outside today. This eternal night has lasted undisturbed for many millions of years. It will continue entirely undisturbed for many millions of years more. The complete lack of visual stimuli promotes deep neural rest. You can simply exist quietly within this peaceful dark space. We activate the low-frequency sonar mapping systems right now. A detailed digital rendering of the seafloor appears on screen. The terrain directly below us is rugged and highly complex. We drift over vast flat fields of pelagic sediment ooze. This soft mud consists of microscopic shells and mineral dust. It has accumulated over countless millennia of incredibly slow deposition. The thick sediment layer muffles any acoustic reflections from below. Volcanic rock outcrops pierce through this soft sedimentary blanket occasionally. Pillow basalts form rounded and bulbous shapes on the bottom. They cooled very rapidly upon contact with the frigid seawater. Geological fracture zones create deep linear trenches in the rock. These deep faults guide the hydrothermal fluids to the surface. We observe massive blocks of lightweight pumice scattered about randomly. They are remnants of explosive underwater volcanic eruptions from antiquity. The mineralogy here differs greatly from typical mid-ocean ridges. High concentrations of iron and manganese stain the surrounding rocks. Sulfide mineral deposits create shimmering metallic patches on the sonar. We detect traces of polymetallic nodules resting in the sediment. These rocky lumps contain valuable copper and cobalt and nickel. They grow at a rate of mere millimeters per million years. In the late 20th century, marine geologists initiated new surveys. The Italian research vessel Urania departed from the Naples harbor. The calendar marked the quiet autumn of the year 1999. Chief scientist Dr. Michael Marni led the ambitious oceanographic expedition. His specialized team targeted the remote Tyrrhenian Sea deep basin. They navigated toward the precise coordinates of 39 degrees 15 minutes north. The longitude reading stood at exactly 14 degrees 20 minutes east. This specific location marked the submerged peak of Marsili Seamount. Researchers deployed a conductivity, temperature, and depth sensor array. This vital instrument is commonly known as a CTD rosette. A heavy steel cable lowered the titanium frame steadily downward. The attached sensors recorded distinct anomalies in the water column. At 500 meters, the water temperature spiked quite slightly. Normal deep Mediterranean water maintains a steady 13 degrees Celsius. The sensitive probes registered local pockets reaching 15 degrees Celsius. This subtle thermal signature suggested active geothermal venting nearby. Chemical sensors also detected elevated levels of dissolved methane gas. Methane heavily indicates the presence of hydrothermal fluid discharge. The team carefully analyzed water samples in the onboard laboratory. Mass spectrometers measured specific isotopes of dissolved helium gas. High concentrations of helium-3 confirmed a deep mantle fluid source. Magma far beneath the crust was actively heating the seawater. The Urania expedition successfully proved the existence of thermal activity. However, they lacked the visual confirmation of actual mineral chimneys. Visual confirmation required a highly advanced remotely operated submersible vehicle. A major technological breakthrough occurred during the summer of 2006. The German research vessel Meteor arrived at the survey site. This massive ship carried specialized equipment for deep ocean mapping. Scientists from multiple European marine institutes joined the historic voyage. They focused their intense search on the nearby Palinuro seamount. Palinuro forms a complex volcanic chain along the dark seafloor. The ship's multi-beam echo sounder mapped the rugged underwater volcanic terrain. Powerful acoustic waves bounced off the rocky basaltic geological formations. Computers rendered a high-resolution three-dimensional map of the summit crater. The digital map revealed unusual spire-like structures on the bottom. These strange geological formations stood out from the surrounding rock. Researchers prepared the remotely operated vehicle for an immediate deployment. The ROV Quest 4000 rested heavily on the aft deck. Technicians completed their final pre-dive safety and mechanical inspections. A massive hydraulic crane lifted the heavy vehicle safely overboard. The thick tether unspooled steadily from the massive steel winch. Quest 4000 descended toward the target depth of 600 meters. High-definition cameras transmitted live digital video back to the ship. Scientists gathered in the dark control room to watch intently. The pressure outside the vehicle measured exactly 60 standard atmospheres. Powerful halogen lights illuminated the barren and rocky volcanic landscape. The robotic vehicle navigated across vast fields of jagged pumice. Suddenly, the live cameras captured a towering solid mineral chimney. Thick gray smoke poured continuously from the top of the structure. The dedicated researchers had finally found the elusive Mediterranean vents. The skilled pilot maneuvered the vehicle closer to the vent. A robotic arm extended a specialized titanium thermal temperature probe. The sensitive probe entered the flowing stream of mineral-rich fluid. Digital displays in the control room showed rapid temperature increases. The superheated fluid exiting the chimney measured 350 degrees Celsius. This extreme heat rivaled the famous mid-ocean ridge black smokers. However, the surrounding water depth was remarkably shallow right here. At 600 meters, ordinary seawater normally boils at 275 degrees. The extremely high salinity of the Mediterranean alters the boiling point. Dissolved heavy salts increase the density and pressure of the fluid. These specific vents release boiling fluids completely rich in heavy metals. The ROV collected physical geological samples of the outer chimney walls. Powerful hydraulic jaws snapped off a piece of the brittle spire. The valuable sample was safely stored inside a specialized collection basket. Later laboratory analysis revealed a completely unique and strange mineralogical composition. Typical deep ocean vents consist primarily of iron and sulfur compounds. These Mediterranean structures contained massive amounts of toxic lead and zinc. Extremely high concentrations of barium sulfate were also clearly present inside. This highly unusual chemistry stems directly from the region's ancient history. Millions of years ago, the entire Mediterranean Sea basin completely evaporated. This catastrophic geological event is known as the Messinian salinity crisis. Thick heavy layers of salt and gypsum blanketed the completely dry basin. When the ocean eventually returned, these evaporites dissolved into the crust. The circulating hydrothermal fluids absorbed these ancient buried salt deposits constantly. This chemical process creates the highly toxic extreme environment seen today. The immense scientific significance of this discovery cannot be easily overstated. Marine geologists realized they had found something completely and totally unprecedented. Radiometric isotopic dating of the chimney structures provided truly shocking results. Detailed chemical analysis of the mineral layers measured their exact age. Most known hydrothermal vents are relatively young and temporary geological formations. Pacific Ocean mineral chimneys typically last for only a few decades. Atlantic Ocean deep vents might persist for several thousand years maximum. The newly discovered Mediterranean vents proved to be significantly much older. Core drill samples showed continuous mineral deposition over immense geological timeframes. Some massive sulfide-based deposits dated back over 2 million years. They currently represent the oldest known active hydrothermal system on Earth. This incredible extreme longevity stems directly from the unique tectonic setting. Mid-ocean ridges spread apart rapidly, constantly destroying all the old vents. The Mediterranean oceanic crust moves at a much slower tectonic pace. Subduction of the African plate occurs at mere microscopic millimeters annually. This highly stable geological environment preserves the incredibly fragile chimney structures. The massive solid sulfide mounds grow undisturbed over countless quiet millennia. The RV Meteor scientific expedition mapped several distinct and separate vent fields. Each mapped field contained dozens of completely active and dormant chimneys. Some extinct mineral spires measured well over 30 meters in height. They stood firmly like silent monuments to ancient and powerful geothermal forces. The currently active vents continued to build entirely new mineral deposits. Scientists accurately estimated the total mineral mass at several millions of tons. This groundbreaking discovery completely reshaped our modern understanding of deep-sea geology. It definitively proved that hydrothermal systems could endure for entire geological epochs. Following the palineuromapping success, researchers greatly expanded their survey area. In 2015, another major scientific expedition targeted the volcanic Aeolian Islands. The Italian research vessel Minerva Uno led this exciting new campaign. They carefully investigated the shallow waters near the small island of Panarea. Precise coordinates 38 degrees 38 minutes north and 15 degrees 4 minutes east guided the large ship. Here, the sandy seafloor drops to a maximum depth of 80 meters. Scuba divers and small autonomous underwater vehicles conducted the initial visual surveys. They quickly discovered a vast network of extremely shallow hydrothermal vents. These shallow vents differed greatly from the deep and dark palinuro structures. Instead of thick black smoke, they released continuous steady streams of gas. Millions of tiny bubbles rose rapidly toward the bright ocean surface above. The escaping gas consisted almost entirely of highly pure carbon dioxide. The surrounding ocean water exhibited extremely high levels of chemical acidity. Sensitive pH sensors recorded values as incredibly low as 5.5 near the vents. This highly acidic environment dissolved the calcium carbonate shells of local mollusks. Scientists quickly realized the Pan-area vents offered a completely unique natural laboratory. They provided a perfectly scaled model for studying global ocean acidification effects. Researchers permanently deployed long-term monitoring stations around the active gas seeps. Sensitive acoustic sensors measured the constant daily volume of escaping gas bubbles. Deep thermal probes tracked the widely fluctuating temperatures of the sandy sediment. The coarse sand around the active vents measured a blistering 130 degrees. Thick white mats of thermophilic bacteria covered the completely hot seafloor. These specialized microorganisms thrived perfectly in the extreme and highly acidic conditions. The Pan-area shallow discovery highlighted the incredible diversity of Mediterranean vent systems. The entire basin hosts both deep black smokers and shallow gas seeps. Exploration of the Mediterranean hydrothermal vents continued well into the modern era. In 2011, the highly famous exploration vessel Nautilus entered the Mediterranean region. Dr. Robert Ballard personally directed this highly publicized and important research mission. The ship featured state-of-the-art telepresence technology for live global scientific broadcasting. Satellite data links transmitted live high-definition video to eager shoreside scientists. The Nautilus crew deployed two highly advanced remotely operated underwater vehicles. The primary ROV, named Hercules, operated in close tandem with ROV Argus. Argus provided bright overhead illumination and wide-angle camera perspectives for the pilots. Hercules performed the highly delicate mechanical maneuvers near the incredibly fragile chimneys. They successfully returned to the deep Palinuro seamount for further detailed study. Hercules carefully mapped the intricate physical details of the massive sulfide mounds. Advanced laser scanners created millimeter-accurate digital computer models of the active vents. The detailed scans revealed highly complex networks of internal fluid flow channels. Scientists clearly observed shimmering hot water leaking from the wide chimney bases. This slow diffuse flow supports entirely different and unique biological animal communities. The Nautilus scientific team also discovered extensive fields of completely extinct vents. These dead mineral chimneys had tragically collapsed into massive piles of oxidized rubble. Iron-rich chemical sediments blanketed the surrounding dark volcanic rocks in bright orange. The expedition successfully collected dozens of high-resolution and pristine geological core samples. These valuable samples provided absolutely crucial data regarding the entire system's evolution. Researchers carefully traced the shifting geographical patterns of hydrothermal activity over time. As immense tectonic stress fractures the crust, underground fluid pathways constantly change. The Mediterranean Sea holds remnants of the ancient Tessis Ocean. This vast body of water existed millions of years ago. Tectonic forces gradually closed this massive prehistoric ocean basin. The current sea represents a shrinking geological environment. Beneath the waves lies the oldest known hydrothermal vent system. Some active venting sites date back over 2 million years. Fossilized chimneys nearby show activity from even earlier epochs. These ancient structures provide a window into past geological eras. The seabed retains a complex memory of continental drift. Researchers study these vents to understand early Earth conditions. The African plate continuously pushes against the Eurasian plate. This massive collision occurs at a very slow pace. The convergence rate measures about 4 millimeters per year. Such slow movement creates a highly fractured ocean crust. The subduction zone curves along the Hellenic volcanic arc. Deep trenches form where the African plate sinks downward. Intense pressure melts the descending rock into liquid magma. This molten material rises toward the Mediterranean seafloor. It pools in shallow chambers beneath the crustal surface. Magma chambers provide the heat source for hydrothermal circulation. The Tyrrhenian Sea functions as a back-arc basin. It formed behind the main subduction zone over time. The crust here stretches and thins out significantly. This extension creates deep faults in the ocean floor. Seawater infiltrates these deep geological fractures quite easily. The Marseille Seamount dominates this underwater tectonic landscape. It stands 3,000 meters above the surrounding basin. This massive volcano stretches 70 kilometers in length. The spreading rate here remains exceptionally slow today. It expands by mere millimeters each passing decade. Volcanic rocks in this region differ from mid-ocean ridges. Basalt is less common in the Mediterranean vent fields. Andesite and rhyolite dominate the local seafloor geology. These rocks contain higher amounts of dissolved silica. The high silica content makes the magma highly viscous. Explosive eruptions occurred here during the Pleistocene epoch. Layers of porous pumice cover much of the seabed. Hydrothermal fluids easily permeate these soft volcanic deposits. The rock matrix acts like a giant geological sponge. This permeability shapes the flow of superheated water. The Palinuro Seamount hosts unique polymetallic sulfide deposits. These mineral structures differ from typical black smoker chimneys. Iron and manganese crusts blanket the upper volcanic slopes. Hydrothermal fluids precipitate valuable metals upon contacting cold seawater. Massive sulfide ores accumulate in thick layers here. The deposits contain high concentrations of lead and zinc. Galena and sphalerite form the primary metallic minerals. Barite crystals grow within the porous sulfide structures. These white crystals contrast sharply with the dark ores. Traces of silver and gold exist within the matrix. In 1999, scientists mapped the Tyrrhenian vent fields. Dr. Michael Mahoney led the initial geological survey. The research vessel Urania deployed advanced multibeam sonar systems. High-resolution maps revealed intricate fault lines and volcanic cones. Later expeditions utilized the French ROV Victor 6000. This submersible collected critical rock samples from the vents. The vehicle operated at depths exceeding 3,000 meters. Video footage showed shimmering water escaping from mineral mounds. Temperature probes recorded fluid venting at 200 degrees Celsius. These measurements confirmed active hydrothermal circulation within the seamounts. The Mediterranean vents release highly acidic hydrothermal fluids. The pH levels often drop below 2.5. This acidity dissolves metals from the surrounding volcanic rocks. The superheated water transports these dissolved elements upward. As fluids exit the seafloor, rapid cooling occurs immediately. The temperature drops from 200 to 14 degrees. This thermal shock forces minerals to precipitate out of solution. Fine particles settle onto the seabed in distinct layers. Over centuries, these mineral layers build massive sulfide mounds. The mounds grow laterally rather than forming tall chimneys. Some Mediterranean vents exist at unusually shallow depths. The Panarea Island complex features vents at 80 meters. These shallow systems release massive amounts of carbon dioxide. Gas bubbles rise continuously through the water column. The geological setting here involves continental crust fragments. This continental influence alters the chemical signature of the fluids. Strontium isotopes in the water match the ancient continental rocks. The shallow vents do not form massive sulfide deposits. Instead, they create extensive fields of white silica crusts. These crusts cement the loose volcanic sediments together. The longevity of the Mediterranean vent systems is remarkable. Typical mid-ocean ridge vents last only a few decades. The Palinuro vents have remained active for thousands of years. Stable magma chambers provide a consistent, long-term heat supply. Thick sediment layers protect the older mineral deposits. The sediments prevent the ores from oxidizing in seawater. Geologists use radiometric dating to determine the deposit ages. Uranium-thorium dating techniques analyze the barite crystal formations. Results show continuous mineral precipitation since the last ice age. This stability makes the region a unique geological laboratory. The Mediterranean basin features a highly fragmented tectonic layout. Microplates rotate and shift between the major continental masses. The Adriatic microplate complicates the regional stress field. Strike-slip faults intersect with the main subduction zones. This structural intersection creates pathways for deep fluid migration. Earthquakes frequently alter the subsurface plumbing of the vents. Seismic activity can open new fractures in the rock. Old fluid pathways often seal themselves with precipitated minerals. The vent locations migrate along the fault lines over time. This dynamic process constantly reshapes the seafloor topography. The mineralogy of these vents reflects the subducted sediments. The sinking African plate carries thick layers of limestone. High temperatures break down these carbonate rocks at depth. This process generates carbon-rich fluids that rise to the surface. Calcium carbonate sometimes precipitates near the vent openings. Aragonite crystals form delicate crusts on the volcanic rocks. The presence of carbonates distinguishes these vents from others. Iron oxides coat the inactive portions of the vent fields. These rust-colored deposits mark ancient fluid flow pathways. The seafloor displays a mosaic of distinct mineral zones. The research vessel Meteor conducted extensive sampling in 2000. Scientists recovered massive sulfide cores measuring several meters long. Geochemist Sven Petersen analyzed the metallic composition of these cores. The data revealed unusual enrichment of trace elements. Antimony and arsenic appear in significant concentrations here. These elements originate from the subducting continental crust. The deep mantle source rock is heavily modified by subduction. Isotope geochemistry traces the exact origin of the venting fluids. The water itself is a mixture of seawater and magmatic vapor. This dual origin creates a complex chemical environment. The Hellenic volcanic arc hosts another group of active vents. The Colombo submarine volcano sits northeast of Santorini. This volcano features a caldera measuring 3 kilometers across. The caldera floor lies 500 meters below the surface. Hydrothermal vents populate the northern rim of this deep crater. The fluids here reach temperatures of 220 degrees. Polymetallic chimneys grow up to 4 meters in height. These structures consist primarily of lead and zinc sulfides. The Colombo vents are much younger than the Tyrrhenian systems. They formed after a massive eruption in 1650. Magmatic degassing drives the hydrothermal activity at Colombo. The underlying magma chamber releases volatile gases continuously. Helium isotope ratios confirm a deep mantle source. The vents emit fluids highly enriched in dissolved gases. Hydrogen sulfide provides chemical energy for the local ecosystem. The steep caldera walls restrict deep ocean water circulation. This isolation creates a stratified water column within the crater. Heavy, mineral-laden fluids pool at the bottom of the caldera. The resulting brine lakes possess extreme chemical properties. These dense pools remain undisturbed by ocean currents. The structural geology of the Mediterranean controls vent distribution. Fault intersections provide the most efficient pathways for fluids. Extensional forces thin the crust to a mere 10 kilometers. This thin crust allows magma to ascend much closer to the surface. The geothermal gradient in this region remains exceptionally high. Heat flows rapidly from the mantle through the rock. Seawater penetrates deeply into the crust along normal faults. The water reaches depths of up to 3 kilometers. At these depths, the water pressure exceeds 300 atmospheres. The fluid remains liquid despite the extreme temperatures. The Mediterranean vent systems document the evolution of a closing ocean. As the continents converge, the basin slowly disappears. The hydrothermal activity represents the final stages of ocean crust formation. Eventually, the African and Eurasian plates will fuse completely. This future collision will thrust the seafloor upwards into mountains. The massive sulfide deposits will become part of a mountain range. Geologists study ancient terrestrial ocean ores known as archaeolites. The Troodos Massif in Cyprus is one such ancient seafloor. The current Mediterranean vents are forming tomorrow's archaeolite deposits. This cycle of creation and destruction defines plate tectonics. The textures of the precipitated minerals reveal their formation history. Rapid thermal cooling creates fine-grained and massive sulfide ores. Slower precipitation allows large, distinct crystals to grow. Dendritic patterns form where fluids mix chaotically with seawater. Banded ores indicate fluctuating temperatures in the hydrothermal system. The mineral layers alternate between iron-rich and zinc-rich bands. These microscopic bands record the pulse of the underlying volcano. Fluid inclusions within the crystals trap ancient water droplets. Scientists extract these microscopic droplets for chemical analysis. The trapped water preserves the exact conditions of past venting. Modern autonomous underwater vehicles currently map these geological features. The AUV Abyss surveyed the Marseille seamount in incredible detail. High-frequency sonar resolved structures as small as 50 centimeters. The bathymetric data revealed hundreds of inactive hydrothermal mounds. Magnetic anomalies point to extensive subsurface alteration of the rock. Hot fluids destroy the magnetic minerals in the original basalt. This localized demagnetization creates a very distinct geophysical signature. Hydrothermal fluid erupts from fractures in the Mediterranean crust. Mineral deposits accumulate around these active tectonic fissures. Decades of mineral precipitation build massive geological structures. These towering mineral chimneys dominate the rugged underwater landscape. Research vessel Nautilus mapped this vent field extensively. High-resolution sonar revealed a complex network of spires. The ROV Hercules captured detailed images of the formations. Black smokers represent the most visually striking features here. Dark plumes of superheated water billow into the ocean. These fluids reach staggering temperatures of 400 degrees Celsius. Extreme pressure prevents the boiling of this liquid. The surrounding seawater remains near a freezing 3 degrees. This massive thermal gradient drives rapid mineral crystallization. Iron and sulfur combine instantly upon meeting cold water. Fine particles of iron sulfide create the black smoke. These dense particles eventually settle on the surrounding rocks. Slowly, the metallic snow builds the chimney walls higher. Some black smoker spires reach 30 meters in height. Geologists measure their growth rates using acoustic transponders. A single chimney can grow several centimeters each day. The internal structure resembles a highly porous metallic sponge. Fluid channels wind chaotically through the mineral interior. Copper and zinc sulfides line the hottest inner conduits. These inner walls endure constant blasting from thermal fluids. Outer layers consist of cooler, more stable anhydrite deposits. Calcium sulfate precipitates to form a rigid structural shell. Dr. Robert Ballard documented these specific mineral gradients. His research team utilized specialized titanium temperature probes. Probes inserted directly into the vent recorded 385 degrees. The fluid composition differs significantly from standard seawater. Magnesium and sulfates are entirely stripped from the water. The hydrothermal solution becomes highly enriched in dissolved metals. Hydrogen sulfide gas saturates the escaping superheated liquid. The pH level drops drastically to a highly acidic 2.8. This acidic nature dissolves metals from the basaltic crust. Submersible Alving collected pristine fluid samples from these orifices. Isobaric gas-tight samplers preserved the fluid at ambient pressure. Laboratory analysis revealed high concentrations of dissolved methane. Silica traces indicate deep interactions with the mantle rocks. White smokers also populate this ancient Mediterranean vent system. These structures emit milky clouds of lighter mineral particles. Barium sulfate and calcium carbonate dominate their chemical makeup. White smoker fluids generally exhibit slightly lower temperature profiles. Thermometers record these emissions between 250 and 300 degrees. The chimneys themselves appear pale gray or stark white. Their formations often lack the rigid verticality of black smokers. White smokers frequently build broad, bulbous mounds of silica. Horizontal flanges extend outward from the main chimney trunks. Hot fluids pool beneath these overhanging mineral ledges. The trapped water creates inverted lakes of superheated liquid. ROV Jason carefully navigated around these fragile mineral overhangs. Cameras captured the shimmering boundary between hot and cold fluids. The refractive index changes sharply at this thermal interface. This optical distortion makes the surrounding water appear wavy. Sonar scans show a distinct spatial distribution of vents. Black smokers cluster tightly along the primary fault lines. White smokers generally occupy the cooler peripheral zones. This distribution reflects the underground plumbing of the system. Magma chambers sit closer to the crust near black smokers. Fluid pathways dictate the surface expression of the vents. Tectonic shifts occasionally alter these deep subterranean channels. An earthquake can instantly extinguish a thriving black smoker. The sudden blockage of fluid halts all mineral precipitation. Without the thermal flow, the chimney begins to decay. Cold seawater gradually oxidizes the exposed iron sulfide structures. The once black walls turn a dull, rusty orange color. Eventually, the brittle spire collapses under its own weight. A mound of metallic rubble marks the extinct vent. New vents frequently open mere meters from dead structures. The Mediterranean floor holds thousands of these collapsed chimneys. Core samples reveal layers of ancient hydrothermal activity. Geologist Dana Yorga mapped these historical deposition layers. Radiometric dating confirms continuous vent activity spanning several millennia. The isotopic signatures match those of ancient oceanic crusts. Some active chimneys display highly complex branching structures. Multiple smaller spires grow outward from a central monolith. This unique morphology strongly resembles a petrified metallic forest. The base of a large chimney can span 5 meters. Thick layers of sulfide mud surround the foundation. Hydrothermal fluids often seep directly through this porous mud. This diffuse flow creates broad areas of warm sediment. Temperature probes in the mud register a steady 50 degrees. The chemical composition of diffuse flow differs from focused venting. Subsea flow mixing dilutes the fluid before it reaches the surface. Dissolved oxygen from seawater interacts with the rising sulfides. This subterranean reaction alters the final chemical output. Scientists utilize mass spectrometers to analyze these subtle differences. The data helps model the entire geothermal circulation system. The pressure at this depth exceeds 200 atmospheres. Such extreme pressure alters the physical properties of water. At 400 degrees, the fluid approaches a supercritical state. Supercritical fluids possess characteristics of both liquids and gases. They dissolve minerals with incredible efficiency and speed. This explains the massive mineral loads carried by the plumes. As the fluid exits the vent, the pressure remains constant. The sudden temperature drop forces immediate chemical precipitation. The resulting mineral grains measure only a few micrometers. Laser diffraction instruments measure the exact size of these particles. The particle size influences how far the ocean currents carry them. Fine iron dust can drift for hundreds of kilometers. This widespread dispersion enriches the broader Mediterranean ecosystem. The vent field covers roughly 3 square kilometers. Researchers divided the area into specific geological sectors. Sector Alpha contains the tallest active black smoker spires. One prominent chimney earned the name Mount Hephaestus. Mount Hephaestus vents fluid at a steady 395 degrees. Its central spire rises 22 meters above the basalt. 3 secondary nozzles vent fluid near the middle section. The structural integrity of such a tall spire is fascinating. Interlocking crystals of chalcopyrite provide necessary mechanical strength. Without this crystalline reinforcement, the strong currents would topple it. Sector Beta features predominantly low-temperature white smoke mounds. The terrain here consists mainly of fractured pillow lavas. Silica deposits fill the deep cracks between the lava formations. The ROV Victor 6000 spent 40 hours surveying Sector Beta. High-definition cameras documented the intricate textures of the anhydrite. The mineral surfaces appear surprisingly smooth and polished. Continuous fluid flow gently erodes the outer crystalline layers. Sector Gamma represents an area of waning hydrothermal activity. Most chimneys here have ceased their mineral emissions entirely. The remaining active vents produce only a weak, clear fluid. This clear fluid indicates a severely depleted mineral concentration. The underground heat source is likely shifting away from gamma. Tectonic plate movements continuously reshape this deep environment. The African plate slowly subducts beneath the Eurasian plate. This massive geological collision generates the necessary thermal energy. Magma rises through the resulting fractures in the oceanic crust. The heat transfers to the deep, circulating seawater aquifers. Geochemists study the specific ratios of helium isotopes here. Helium-3 indicates a direct connection to the Earth's mantle. The Mediterranean vents show unusually high helium-3 concentrations. This confirms the deep origins of the hydrothermal fluids. The chemistry also reveals traces of rare earth elements. Neodymium and europium are detected in the massive sulfide deposits. These elements provide clues about the composition of the mantle. Extracting these core samples requires specialized robotic drilling equipment. Diamond-tipped drill bits slowly penetrate the hardened sulfide crust. The drill must withstand the extreme heat of the interior. Water cooling systems prevent the robotic mechanisms from melting. A successful core sample extracts a pristine mineral cylinder. The cross-section reveals concentric rings of different colored minerals. These rings chronicle the fluctuating temperatures of the vent's history. Dark inner rings signify periods of intense, high-temperature venting. Lighter outer bands indicate cooler, silica-rich deposition phases. This geological record functions much like the rings of a tree. Scientists can read the lifespan of a chimney through these bands. Some larger structures show evidence of multiple reactivation cycles. A chimney might go dormant for several decades. A new seismic event can suddenly reopen the blocked channels. Fresh superheated fluid blasts through the old mineral shell. The growth process begins anew on the existing foundation. The physical dynamics of the plume are highly complex. The superheated fluid rises rapidly due to extreme buoyancy. It shoots upward from the vent orifice at high velocity. The initial jet phase maintains a tight, focused vertical column. Surrounding seawater begins to mix into the rising thermal plume. This entrainment process gradually cools the ascending fluid mixture. The plume eventually reaches a level of neutral buoyancy. It stops rising and spreads horizontally across the ocean layer. This horizontal spreading creates a massive chemical cloud underwater. Oceanographers track these massive chemical clouds using sensitive nephelometers. Nephelometers measure the optical scattering caused by suspended particles. The data maps the far-reaching influence of the vent field. The plume from Mount Hephaestus stretches for over 5 kilometers. It hovers roughly 200 meters above the seafloor. Deep ocean currents slowly disperse the suspended mineral particulate. The chemical composition changes as the plume travels outward. Heavier iron particles fall out of suspension relatively quickly. Lighter manganese compounds remain dissolved for much longer periods. This creates a predictable spatial gradient of chemical deposition. The seafloor sediment reflects this gradual fallout pattern perfectly. Researchers collect sediment cores at varying distances from the vents. The core analysis confirms the predicted dispersion models. The vent structures also feature complex microtopography on their surfaces. Small mineral flanges create miniature terraces along the chimney walls. Tiny secondary ventlets sprout from the sides of major spires. These miniature vents release small trickles of hot fluid. The Mediterranean hydrothermal system presents a highly unusual chemical signature. Ancient geological events heavily influence the current vent fluid composition. 6 million years ago, the Messinian salinity crisis occurred here. Thick layers of evaporite salts precipitated across the entire basin. Modern hydrothermal fluids must travel through these massive salt deposits. This interaction fundamentally alters the emerging chemical profile. Ambient Mediterranean deep water already exhibits elevated salinity levels. Background ocean salinity typically hovers around 35 practical salinity units. Here, the baseline salinity reaches 38.5 units. However, the vent emissions shattered these standard oceanographic measurements. Fluid emerging from the primary chimneys is incredibly dense. Salinity near the discharge zones approaches 300 units. This creates an extreme hypersaline environment around the active fissures. Dense brine pools form within the depressions near the vents. These heavy fluids settle into the bathymetric lows. Standard ocean currents cannot easily disperse these concentrated chemical pools. The physical boundary between normal seawater and brine is sharp. Scientists call this distinct separation layer a halocline. Instruments crossing this barrier register immediate and drastic chemical shifts. Acidity levels at these Mediterranean sites vary quite dramatically. Most global hydrothermal vents emit slightly acidic fluid. The East Pacific rise typically produces fluids around pH 4. Mediterranean volcanic vents often display far more extreme pH values. Samples collected near the Palinuro seamount show remarkable acidity. Sensors on the ROV Victor 6000 recorded extremely low pH. The exact measurement showed a pH of 2.8. This highly acidic fluid dissolves surrounding carbonate structures instantly. The corrosive nature of the water shapes the local geology. Conversely, some nearby low-temperature seepage areas exhibit alkaline traits. These specific alkaline sites register pH values above 8. This stark chemical contrast exists within a single geological region. Researchers from the National Institute of Oceanography documented this anomaly. Dr. Roberto D'Annavaro led several key expeditions to these sites. His team utilized advanced mass spectrometers to map the chemistry. They discovered a complex mosaic of shifting pH gradients. The acidic fluids carry high concentrations of dissolved heavy metals. Iron and manganese remain soluble in these low pH environments. As the acidic fluid mixes with seawater, minerals rapidly precipitate. This precipitation forms the structural foundation of the vent chimneys. Hydrogen sulfide represents a critical component of this vent ecosystem. The concentration of this compound here is exceptionally high. Magma beneath the crust heats circulating seawater to extreme temperatures. Sulfate from the seawater reacts with iron-rich crustal rocks. This thermochemical sulfate reduction generates massive amounts of hydrogen sulfide. Measurements indicate sulfide concentrations exceeding 12 millimoles per liter. This vastly outpaces the output of the Mid-Atlantic ridge vents. Mid-Atlantic sites generally produce less than 5 millimoles per liter. The Mediterranean fluids are highly toxic to most marine life. Dissolved hydrogen sulfide strips oxygen from the surrounding water column. This chemical reaction creates localized zones of complete anoxia. Oxygen levels drop to zero within meters of the discharge. Specialized titanium sampling bottles capture these volatile fluids under pressure. If brought to the surface unsealed, the gases would escape. During a recent expedition, the RV Meteor deployed these samplers. Chemists aboard analyzed the pristine fluid samples in pressurized laboratories. They identified unique sulfur isotopes within the captured vent water. These isotopes trace the exact geological origin of the sulfide. The data confirms heavy interaction with deep mantle rocks. Methane gas bubbles constantly escape from the fractured seafloor. The volume of methane released here puzzles marine geochemists. Most hydrothermal methane originates from a process called serpentinization. Water reacts with olivine minerals in the deep oceanic mantle. This abiotic reaction produces hydrogen gas and subsequent methane. However, Mediterranean methane possesses a distinct isotopic signature. Carbon-13 analysis reveals a complex origin for these gases. A significant portion of the methane is actually thermogenic. Intense subterranean heat cooks ancient organic matter buried in sediments. This thermal degradation cracks complex hydrocarbons into simple methane molecules. The gas then migrates upward through the porous volcanic rock. Methane concentrations in the fluid exceed 20 millimoles per liter. This is nearly double the concentration found at Lost City. The Lost City hydrothermal field is famous for methane production. Yet, this ancient Mediterranean system surpasses those well-known Atlantic levels. Acoustic sonar easily detects the rising plumes of methane gas. The bubbles create strong acoustic reflections on the ship monitors. Researchers map these gas flares to locate hidden vent structures. Comparing this site to global vents highlights its unique nature. The East Pacific Rise features fast-spreading tectonic plates. Those Pacific vents produce extremely hot black smoker fluids. Temperatures there routinely exceed 350 degrees Celsius. The Mediterranean system operates under entirely different tectonic constraints. This is a convergent boundary zone with complex subduction mechanics. Fluid temperatures here generally peak around 200 degrees Celsius. Despite lower temperatures, the chemical enrichment is paradoxically higher. The slow fluid migration allows prolonged interaction with crustal rocks. This extended contact time maximizes mineral dissolution into the water. Indian Ocean vents generally show very high hydrogen concentrations. Mediterranean vents match that hydrogen output but add extreme salinity. The combination of hypersalinity and high methane is virtually unmatched. Only the Red Sea deep basins share similar chemical characteristics. However, the Red Sea lacks the direct volcanic vent interactions. This makes the Mediterranean sites a unique oceanographic laboratory. In past decades, major international research initiatives targeted this area. The French Research Institute IFREMA provided critical deep-sea technology. Their remotely operated vehicle captured high-resolution chemical data. Sensors measured dissolved organic carbon near the active venting chimneys. The organic carbon levels were surprisingly high for this depth. Subsequent dives by the submersible Alvin confirmed these initial findings. Alvin navigated precisely to coordinates 39 degrees north. The longitude was approximately 14 degrees east of the meridian. The submersible operated at a depth of 3,000 meters. It extended its robotic manipulator arm toward the fluid flow. A temperature probe recorded 198 degrees Celsius. Simultaneously, a mass spectrometer analyzed the dissolved gas ratios. The ratio of helium isotopes indicated clear mantle fluid contributions. Helium-3 is a primordial isotope trapped since Earth formed. Its presence proves the fluids originate deep within the lithosphere. Dr. Nicole Dubilier studied the chemical energy available here. Her research focused on the sheer volume of reduced compounds. The vent fluid provides a massive, continuous chemical energy source. Trace metals dissolved in the fluid offer further scientific insights. Zinc and copper concentrations reach anomalous levels in these waters. The corrosive acidic fluid strip these metals from basaltic rocks. As the fluid cools upon exit, metal sulfides rapidly form. These microscopic metallic particles create a dense, cloudy suspension. Unlike Pacific black smokers, these plumes have a yellowish tint. The yellow hue results from the overwhelming elemental sulfur content. Free sulfur precipitates instantly when contacting the cold ambient ocean. The surrounding seawater temperature is roughly 13 degrees Celsius. This is unusually warm for deep ocean environments globally. Atlantic deep waters typically hover around 2 degrees Celsius. The enclosed nature of the Mediterranean basin traps geothermal heat. This elevated background temperature alters the precipitation thermodynamics. Minerals crystallize at different rates compared to colder ocean basins. Barium and strontium compounds also emerge from the vent fissures. These elements form intricate, fragile crystalline structures around the orifices. The barite chimneys grow mere millimeters over several long decades. Geochemists utilize radioactive isotopes to date the vent fluid circulation. Radium isotopes provide a reliable chronometer for these underwater systems. Analysis shows the water spends decades circulating through the crust. This slow percolation process concentrates the dissolved mineral load significantly. Lithium isotopes reveal the exact temperature of the subterranean reactions. The isotopic fractionation of lithium depends entirely on ambient heat. Calculations suggest subsurface reaction zones exceed 400 degrees Celsius. The fluid cools significantly as it ascends through the crust. By the time it vents, it loses half its heat. Yet, it retains the chemical signature of the deeper inferno. Dissolved silica concentrations further corroborate these high subsurface temperature estimates. Silica solubility increases exponentially with rising pressure and thermal energy. The venting fluids are completely supersaturated with dissolved quartz compounds. Amorphous silica coats the surrounding basaltic rocks in smooth layers. This glassy coating seals older fractures in the ocean floor. The sealing process forces hydrothermal fluids to find new pathways. This causes the active venting zones to migrate over time. The interaction between hydrothermal fluid and brine requires careful study. The dense brine pools act as massive chemical retention traps. Normally, ocean currents sweep away dissolved vent chemicals quite rapidly. Here, the heavy salt water prevents upward vertical chemical mixing. Hydrogen sulfide accumulates in the brine pool for many centuries. The resulting chemical environment is entirely devoid of dissolved oxygen. Nitrate and nitrite compounds are also completely absent here. Instead, ammonium reaches incredibly high concentrations within the stagnant fluid. Ammonium levels exceed anything measured in the open Atlantic Ocean. The chemical stability of these deep anoxic lakes is remarkable. They remain undisturbed by seasonal changes on the ocean surface. The interface between the brine and seawater is chemically turbulent. Microeddies form where the two distinct water masses gently meet. Complex oxidation reactions occur strictly along this millimeter-thin boundary layer. Manganese oxidizes rapidly at this specific chemical transition zone. This creates a suspended layer of dark particulate matter above. Laser spectrometers easily detect this horizontal band of suspended particles. The Mediterranean hydrothermal system represents a perfect geochemical storm. Ancient salt deposits dictate the extreme salinity of the fluids. Tectonic friction generates the necessary heat for deep mineral dissolution. Thick sediment layers provide the organic material for thermogenic methane. The ROV Victor 6000 illuminates the Palinuro seamount. Sensors record a depth of 600 meters exactly. Hydrothermal fluids seep through fractured volcanic crust here continually. White microbial mats cover the uneven basaltic seafloor entirely. These bacterial colonies form the primary biological food source. Dr. Roberto D'Annavaro studied this unique ecosystem quite extensively. He documented heavy concentrations of specialized thiotropic bacteria. They thrive in temperatures reaching 60 degrees Celsius easily. Filamentous Beggiatoa bacteria create thick carpets across submerged rocks. These mats reach thicknesses of 3 full centimeters. They extract energy from toxic hydrogen sulfide emissions naturally. This process is known as deep marine chemosynthesis. The total microbial biomass is surprisingly high here. Researchers measured 30 grams of carbon per square meter. Such density sustains a beautifully complex web of life. Tiny grazing organisms navigate the dense bacterial forests constantly. Nematode worms dominate the microscopic faunal community completely. Over 200 distinct nematode species coexist peacefully here. The genus Tarvea represents a significant endemic population. These microscopic worms exhibit highly unique morphological adaptations. They lack functional eyes in this completely aphotic environment. Their bodies contain specialized organs for detoxifying harmful sulfides. Population densities reach 4,000 individuals per square meter. This concentration far exceeds typical deep Mediterranean abyssal basins. Dr. Cinzia Coronel DC analyzed these rich sediment samples carefully. Her team discovered entirely new branches of marine life. Many recorded species exist nowhere else on our planet. The isolation of the Mediterranean Sea drives this endemism. Millions of years of separation forged unique genetic pathways. These hydrothermal vents act as evolutionary incubators for specialists. Larger invertebrates also populate the active hydrothermal discharge zones. The bivalve Leucinoma kazani rests partially buried nearby. This clam relies entirely on symbiotic bacterial partners. Specialized gill tissues house millions of sulfur-oxidizing microbes safely. The host provides oxygen and sulfide to the bacteria. In return, microbes synthesize essential organic carbon compounds. Leucinoma kazani forms dense beds near the fluid seeps. Scientists count exactly 50 clams per square meter here. Their white shells contrast sharply against dark volcanic sediment. The RV Meteor collected several specimens during Expedition M36. Dr. Michael Turkay catalogued their unique anatomical structures meticulously. He noted a significant reduction in their digestive tracts. This regression indicates complete reliance on microbial symbionts. These bivalves filter water efficiently at very low temperatures. They prefer fluid mixtures around 15 degrees Celsius. Slender tubes emerge from the mineral-rich vent chimneys. These structures belong to the polychaete Spiochetopterus solitarius. This tube worm represents another crucial endemic biological species. Unlike Pacific giant tube worms, these remain quite small. Their tough chitinous tubes measure only 10 centimeters long. They filter suspended organic particles from the water column. Delicate feeding appendages extend from their narrow tube openings. These tentacles retract instantly at the very slightest disturbance. ROV cameras captured their rapid withdrawal mechanisms perfectly. Spiochetopterus solitarius forms vast meadows on flat rock surfaces. Biomass calculations show 15 grams per square meter. This figure indicates a highly productive local marine ecosystem. Other polychaete worms crawl among the protective outer tubes. The species Cyboglinum feudicum thrives in cooler peripheral zones. They absorb dissolved organic matter directly through their skin. Scavenging crustaceans patrol the edges of the bacterial mats. Small amphipods feed on decaying biological material continuously here. The species Ventiella sulphuris represents a highly dominant scavenger. These tiny shrimp-like creatures navigate the steep thermal gradients. They tolerate sudden temperature shifts up to 30 degrees. Their specialized hemoglobin binds oxygen with extreme chemical efficiency. This internal adaptation allows survival in hypoxic vent fluids. Researchers observe them gathering around inactive mineral chimney structures. They form dense swarms of several hundred individuals. Larger decapod crabs occasionally visit the active vent sites. The Mediterranean crab Chasseon mediterraneus hunts near the periphery. These predators target weakened bivalves and slow polychaete worms. Their movements remain deliberate and incredibly energy efficient. They rarely enter the hottest fluid discharge areas. Severe thermal stress limits their hunting territory significantly. Siliceous sponges anchor themselves firmly to exposed volcanic rocks. The species Asbestopluma hypogea represents a truly fascinating adaptation. This carnivorous sponge lacks a traditional filter-feeding biological system. It uses microscopic hooks to capture passing crustacean prey. Long filaments radiate from its central structural stalk. These filaments ensnare tiny copepods drifting in deep currents. The sponge gradually envelops its struggling prey completely. Cellular digestion occurs slowly over several consecutive days. This predatory lifestyle conserves energy in extreme deep environments. Dr. Jean Vaislet first described this remarkable feeding strategy. He studied rare specimens collected from the Marseilles seamount. These sponges maintain a very low local population density. Only 2 individuals exist per square meter of rock. Their total biomass remains a fraction of the bivalves. Yet they play a crucial role as apex micropredators. Distinct biological zones form naturally around the hydrothermal vents. Temperature gradients dictate the specific distribution of all species. The hottest central areas host only hyperthermophilic archaea strains. These microbes survive fluid temperatures exceeding 100 degrees. The strain Pyrococcus furiosus multiplies rapidly in boiling water. Their cellular enzymes remain stable under extreme thermal stress. Moving outward, the water temperature drops to 60 degrees. Here, the white Beggiatoa mats dominate the landscape entirely. These filamentous bacteria oxidize hydrogen sulfide for vital energy. Further out, yellow microbial patches indicate different bacterial strains. The genus Thiothrix prefers ambient temperatures around 40 degrees. These distinct yellow mats support the highest nematode densities. At 20 degrees, the larger bivalve communities begin appearing. This precise thermal zonation creates concentric rings of life. Scientists map these biological rings using acoustic multibeam sonar. The Aeolian Arc hosts another cluster of shallow vents. Near Panaria Island, vents release massive volcanic gas plumes. Carbon dioxide bubbles constantly stream from the fractured seafloor. These emissions create highly acidic local marine environments. The surrounding water pH drops to an extreme 5.5. Most calcifying organisms cannot survive such harsh corrosive conditions. Normal clam shells would dissolve rapidly in this water. However, specific extremophiles have adapted to this severe acidity. A unique strain of cyanobacteria forms thick orange mats. These photosynthetic microbes utilize dim light penetrating the shallows. They coexist with chemosynthetic bacteria in a dual ecosystem. Small gastropods graze cautiously on these acidic bacterial mats. The snail Tritia neratia exhibits unusually thick protective shells. This extra calcification prevents dissolution from the acidic water. Researchers from the University of Palermo monitor these snails. The Mediterranean vent systems demonstrate truly remarkable ecological stability. Fossil records indicate continuous hydrothermal activity for many millennia. Some mineralized microbial mat structures date back 10,000 years. This longevity allows highly specialized symbiotic relationships to evolve. The RV Urania extracted sediment cores from the Marsili Basin. Isotope analysis revealed highly consistent biological production over time. Carbon-14 dating confirmed the ancient origins of these communities. The vent fauna remains isolated from global ocean currents. The shallow Strait of Gibraltar acts as a biological barrier. Deep water larvae cannot cross this shallow geographical threshold easily. Atlantic vent species never colonize Mediterranean hydrothermal sites successfully. This strict isolation preserves the ancient genetic lineage perfectly. The Mediterranean vents function as a closed ecological loop. Nutrients recycle efficiently within the immediate active vent vicinity. Dead organic matter sinks back into the hungry microbial mats. Scientific researchers continue discovering novel microbial strains here. A unique archaean was isolated from the Palaneuro vents. Scientists named it Thermococcus mediterraneus after its geographic home. This organism processes complex proteins at 80 degrees Celsius. Its metabolic pathways differ from all known Pacific strains. Marine biotechnologists study these enzymes for potential industrial applications. The DNA polymerase from this archaean copies genetic material. It maintains high accuracy even at extreme fluid temperatures. Another bacterium, Caminibacter mediterius, reduces nitrate for metabolic energy. It flourishes in the warm, oxygen-depleted subsurface vent fluids. These microscopic entities form the invisible biological foundation here. Without them, the entire vent ecosystem would collapse instantly. They convert toxic inorganic chemicals into usable biological energy. This primary production rivals sunlight-driven photosynthesis in sheer efficiency. The dark ocean floor blooms with invisible cellular activity. Total biomass at these vents defies early scientific expectations. Initial surveys predicted barren landscapes due to geographical isolation. Instead, the biological density mirrors rich coastal marine estuaries. A single square meter yields thousands of tiny organisms. The combined wet weight often exceeds 2 full kilograms. This concentration stands out against the surrounding deep sea. Non-vent Mediterranean depths average less than 1 gram per meter. Hydrothermal energy concentrates life into tight, highly productive oases. The spatial extent of these communities remains quite limited. Most active vent fields span less than 100 meters. Beyond this radius, the biological density drops off precipitously. The sharp transition zone measures merely a few centimeters. Organisms must stay within the warm, chemical-rich fluid flow. Drifting too far results in rapid starvation and freezing. Survival demands strict adherence to the invisible hydrothermal gradients. The deep submersible Alvin never visited the Mediterranean vents. Instead, European ROVs conduct the majority of biological surveys. The Italian research vessel Minerva Uno maps new locations. High-definition cameras document the fragile tube worm meadows perfectly. Laser scalers measure the exact dimensions of microbial mats. These precise measurements help track annual growth rates accurately. Scientists observe slow but steady expansion of bacterial colonies. The Leucinoma bivalves reproduce during the late summer months. Larvae disperse through the water column using thermal currents. They settle on newly formed basaltic rock surfaces nearby. This constant cycle of renewal sustains the ancient ecosystem. Conservation efforts now focus on protecting these unique habitats. Deep-sea mining poses a potential threat to vent communities. The Palinuro seamount contains valuable massive sulfide mineral deposits. Preserving these endemic species requires ongoing international scientific cooperation. The Mediterranean Sea hosts a highly unusual deep marine ecosystem. This ancient basin remains almost completely enclosed by surrounding landmasses. Such extreme geographic isolation drives entirely unique evolutionary biological pathways. Deep waters here are unusually warm for the benthic ocean. Ambient temperatures hover steadily around 13 to 14 degrees Celsius. Most global deep ocean basins measure near a freezing 2 degrees. This significant thermal anomaly permanently shapes the entire vent community. Scientists aboard the research vessel Urania thoroughly documented this phenomenon. They deployed advanced remotely operated vehicles into the Tyrrhenian Sea. The massive Marseille seamount hosts several active hydrothermal vent fields. These specific geological vents release fluids at 200 degrees. The surrounding ambient water quickly cools these highly toxic emissions. A steep chemical gradient immediately forms near the vent chimney. This specific gradient supports a specialized and highly independent food web. Chemosynthesis entirely replaces photosynthesis in this permanently sunless oceanic abyss. Microbes form the foundational biological layer of this dark ecosystem. They extract vital energy directly from dissolved inorganic chemical compounds. Hydrogen sulfide serves as the primary energy currency for life. Methane gas also provides essential carbon for these microscopic organisms. Giant white microbial mats completely cover the surrounding basaltic rocks. These extensive biological mats consist mostly of Beggiatoa bacterial species. Marine biologist Dr. Roberto D'Annavaro studied these specific bacterial strains. His research team measured microbial biomass near the Pan Area vents. The density of microscopic life here rivals tropical coral reefs. Yet no sunlight ever reaches these extreme Mediterranean Ocean depths. Biological energy flows upward purely from the microscopic chemical level. Bacteria efficiently oxidize toxic environmental sulfides into harmless sulfate compounds. This continuous chemical reaction releases pure energy for cellular growth. Larger organisms consume these thriving bacterial mats directly for sustenance. Other creatures incorporate the microbes directly into their own tissues. This internal symbiotic relationship defines long-term survival at the vents. Small specialized bivalves dominate the Mediterranean hydrothermal vent peripheral zones. The clam family Leucinidae is particularly abundant in this region. These unique clams house sulfur-oxidizing bacteria deep within their gills. The host animal provides the bacteria with steady chemical access. In return, the internal microbes produce complex organic carbon molecules. This synthesized carbon consistently feeds the host clam from within. Scientists carefully collected these delicate specimens using the ROV Victor 6000. They analyzed the stable carbon isotopes within the clam tissues. The precise isotopic signature proves a purely chemosynthetic daily diet. These deep clams do not rely on falling marine snow. They remain entirely disconnected from the sunlit surface world above. Mediterranean vents notably lack the giant fauna of other oceans. You will not find massive Rifsha tubeworms in this basin. Giant hydrothermal vent clams are also distinctly absent from here. The shallow Strait of Gibraltar acts as a massive biological barrier. Deep water ocean currents cannot easily cross this elevated underwater sill. Atlantic vent species simply cannot migrate into the Mediterranean basin. This physical restriction created a highly endemic and isolated ecosystem. The organisms residing here evolved primarily from shallow water coastal ancestors. They slowly adapted to the deep vent environment over millennia. The Messinian salinity crisis heavily influenced this specific evolutionary path. 5 million years ago, the Mediterranean Sea almost completely evaporated. This catastrophic geological event wiped out ancient deep-sea marine life. The current vent fauna represents a relatively recent biological colonization. They survived by finding refuge near these chemical thermal oases. Tiny polychaete worms form complex colonies near the fluid exits. The genus Cyboglinum is frequently observed by deep marine biologists. These slender worms completely lack a functional internal digestive tract. They rely entirely on endosymbiotic bacteria for all their nutrition. Their fragile protective tubes cluster around gentle diffuse flow zones. The water temperature here measures roughly 30 to 40 degrees. This specific thermal range perfectly optimizes internal bacterial metabolic rates. Nutrient transfer rates are carefully measured by advanced chemical sensors. The ROV Hercules recorded these precise thermal gradients during expeditions. Fluid samples show incredibly high concentrations of dissolved iron particles. Manganese is also highly abundant in these specific vent emissions. These heavy metals support entirely distinct lithotrophic bacterial microbial communities. Iron oxidizing bacteria create striking bright orange deposits on the rocks. These mineral crusts provide a solid foundation for biological settlement. Energy moves highly efficiently through this simplified deep food web. Secondary consumers graze directly on the thick white bacterial mats. Small gastropod snails scrape microbes from the solid mineral chimneys. Their specialized dewlers are perfectly adapted for this hard surface. Microscopic nematode worms thrive deep within the thick microbial layers. They navigate the tiny microscopic spaces between dense bacterial filaments. This microscopic grazing keeps the bacterial populations healthy and active. Marine biologist Dr. Nicole Dubilier analyzed these complex microhabitats extensively. Her detailed research revealed multiple layers of intricate symbiotic interactions. Some specific nematodes carry their own protective episymbiotic outer bacteria. These helpful bacteria completely coat the outer cuticle of the worms. They actively detoxify the immediate harsh environment for their host. This represents a highly specialized and successful evolutionary survival adaptation. Survival here requires constant biochemical negotiation with highly toxic chemistry. Larger mobile predators constantly patrol the outer edges of the vents. Deep-sea crabs carefully navigate the warm and toxic fluid streams. They belong specifically to the specialized biological family called Bythagriidae. These crabs are completely blind but possess highly acute chemical sensors. They easily detect the faint scent of damaged tissue from afar. Their daily diet consists mostly of dead or dying organisms. They act as the primary biological scavengers of this ecosystem. Small specialized shrimp also gather densely around the venting fluids. They do not possess the specialized dorsal eyes of Atlantic shrimp. Mediterranean vent shrimp rely entirely on tactile and chemical sensory cues. They feed constantly on the bacterial mats and small invertebrates. Their overall population density is much lower than Pacific counterparts. The highly limited active vent area restricts their total numbers. They maintain a delicate biological balance with their limited food supply. The Palinuro seamount offers another entirely unique deep ecological zone. It is located at a depth of roughly 600 meters. This relatively shallow depth allows a tiny fraction of light penetration. However, the local vent community remains strictly and purely chemosynthetic. The hydrothermal fluids emitted here are incredibly and highly acidic. The local water pH level frequently drops far below 3. Most normal marine life would quickly dissolve in such acidic conditions. The local endemic fauna evolved incredibly thick protective outer cuticles. Standard calcium carbonate shells are extremely difficult to maintain here. Some specialized bivalves utilize an organic periostracum layer for defense. This tough outer skin protects their fragile shells from rapid dissolution. Scientists from the IFRMA Institute carefully documented this unique adaptation. They used specialized titanium probes to measure the fluid acidity. These durable probes easily withstand the highly corrosive deep ocean environment. Methane seeps often co-occur with hydrothermal thermal activity in this region. This pairing creates a highly complex dual-energy deep marine ecosystem. Methanotrophic bacteria eagerly consume the constantly bubbling methane gas emissions. They form incredibly dense communities right alongside the sulfur oxidizers. Solid carbonate crusts naturally precipitate as a byproduct of this consumption. These newly formed hard substrates provide crucial anchor points for sessile organisms. Deep sea sponges firmly attach themselves to these newly formed rocks. These sponges continuously filter suspended bacteria from the surrounding water column. The gentle water currents distribute these microbes over very short distances. Localized thermal eddies keep the vital nutrients near the vent source. This highly efficient retention system easily sustains the large biological biomass. The entire Mediterranean vent ecosystem operates as a completely closed loop. Very little organic matter ever escapes into the broader ocean basin. Energy is endlessly recycled among the highly specialized resident organisms. The Mediterranean basin functions perfectly as an isolated natural laboratory. It demonstrates exactly how marine ecosystems develop in strict isolation. The complete lack of tidal forces creates a highly stable environment. Deep ocean currents are driven entirely by subtle water density differences. Local salinity and temperature dictate the slow movement of water masses. This extreme physical stability allows delicate symbiotic biological relationships to persist. The local speciation rate is carefully tracked by international marine geneticists. Advanced DNA sequencing reveals significant evolutionary divergence from Atlantic relatives. The genetic mutation rates align perfectly with the basin's geological history. Researchers estimate a biological separation time of nearly 3 million years. This prolonged genetic drift produced entirely new genera of marine life. Surface ocean seasons do not ever affect this deep marine ecosystem. Spring phytoplankton blooms far above have absolutely no impact on vent life. The localized chemical food supply remains perfectly constant all year round. Tectonic seismic shifts occasionally disrupt this highly stable deep environment. Earthquakes along the deep fault lines can suddenly alter fluid pathways. A sudden catastrophic loss of flow will quickly destroy a local community. The symbiotic bacteria perish entirely within a matter of a few days. Larger dependent organisms starve shortly after the vital microbes disappear completely. However, entirely new hydrothermal vents frequently open up very close nearby. Hardy pioneer species quickly colonize these completely fresh deep fluid sources. Free-living bacterial microscopic larvae drift silently in the slow bottom currents. They easily detect the faint chemical signature of new hydrothermal activity. They quickly settle on the bare basaltic rock and multiply incredibly rapidly. A brand new thriving ecosystem establishes itself within just a few months. This endless geological cycle of biological destruction and renewal is completely continuous. Studying this unique ecosystem requires highly specialized and advanced marine technology. European marine research consortiums utilize advanced robotic systems for this task. Oceanographic research in the Mediterranean requires precise technological coordination. The National Institute of Geophysics and Volcanology leads many efforts. Italian scientists began mapping the Marsili Seamount in 1999. The research vessel Urania served as the primary command center. Oceanographer Michael Mahoney directed this comprehensive bathymetric survey. The team utilized high-resolution multibeam sonar for the first time. Sound waves mapped the complex topography of the ancient volcano. Marseille rests at coordinates 39 degrees north and 14 degrees east. The summit reaches a depth of 500 meters. The base extends down to 3,000 meters below sea level. Sonar readings revealed anomalous plumes rising from the seafloor. These plumes indicated active hydrothermal venting along the volcanic ridges. The Urania deployed water sampling rosettes to capture the fluids. Chemical analysis showed high concentrations of dissolved iron and manganese. This mission established Marseille as a crucial hydrothermal research site. Subsequent expeditions focused on the nearby Palinuro seamount. The German research vessel Meteor arrived at the site in 2006. Scientists aimed to understand the subsea flow mineral deposits. They deployed a portable remotely operated drill rig. The drill penetrated the sulfide mounds covering the vent field. Core samples revealed layers of ancient hydrothermal activity. Geochemists measured fluid temperatures reaching 60 degrees Celsius at the surface. Subsurface reservoir temperatures likely exceed 300 degrees Celsius. The drilling operation recovered massive sulfide ores rich in copper. Lead and zinc concentrations matched those of oceanic spreading centers. This discovery proved the Mediterranean vents hold significant geological value. Researchers catalogued the mineralogical data in international oceanographic databases. The Palinuro cores provided a timeline of volcanic vent evolution. Isotope dating showed continuous hydrothermal activity for thousands of years. Exploring these shallow yet complex vents requires advanced robotics. The ROV Victor 6000 played a vital role in later missions. This French-built submersible features high-definition cameras and manipulator arms. Pilots control the vehicle from a surface ship via fiber optic cables. Victor 6000 captured the first detailed images of Mediterranean vent chimneys. The robotic arms delicately collected fragile sulfide structures. Scientists equipped the ROV with in-situ mass spectrometers. These instruments analyze fluid chemistry directly at the vent orifice. Real-time data transmission allows immediate adjustments to the sampling strategy. The mass spectrometer detected traces of methane and hydrogen sulfide. Dissolved carbon dioxide levels varied significantly between different vent sites. Researchers also deployed autonomous underwater vehicles for broader surveys. The AUV*X mapped the chemical halos surrounding the vent fields. These autonomous missions operate silently above the hydrothermal systems. Short expeditions provide only brief glimpses of vent dynamics. Scientists needed continuous data to understand long-term geological processes. The European Multidisciplinary Seafloor and Water Column Observatory was created. EMSO represents a massive network of cable deep-sea observatories. The Western Ionian Sea node monitors the Mediterranean tectonic activity. Heavy armored cables connect the seafloor instruments to coastal stations. These cables supply constant power and transmit high-bandwidth data. Hydrophones record the acoustic signatures of fluid venting. Seismometers detect tiny micro-earthquakes within the deep volcanic crust. Pressure sensors monitor tidal influences on hydrothermal fluid flow. Temperature probes record minute fluctuations in the vent emissions. This continuous monitoring reveals unexpected patterns in vent behavior. Scientists discovered that distant earthquakes can alter local vent flow. The EMSO network operates without interruption throughout the entire year. Biological sampling forms another crucial aspect of these expeditions. Microbiologist Teresa Gubbe studied the unique bacterial communities found here. The research vessel Minerva Juno hosted a dedicated biological mission. Scientists used specialized titanium syringes to collect uncontaminated water samples. The ROV Hercules maneuvered these syringes into the vent fluid stream. The samples were immediately transferred to high-pressure incubation chambers. These chambers simulate the extreme conditions of the deep seafloor. Researchers successfully cultured thermophilic bacteria from the Mediterranean vents. DNA sequencing revealed distinct genetic variations from Atlantic vent microbes. The isolation of these ancient hydrothermal systems drives rapid evolutionary divergence. Scientists identified novel enzymes within the bacterial cell structures. These enzymes function efficiently in highly acidic and warm environments. The biological data contributes greatly to our understanding of early life. Geochemical tracing techniques advanced significantly during the past decade. Researchers introduced rare earth element analysis to study vent fluids. The research vessel El Atalant conducted a comprehensive geochemical survey. Scientists deployed benthic landers equipped with highly sensitive chemical sensors. These landers sink to the seafloor and remain for months. They periodically sample the water column directly above the vent field. The sensors detect minute changes in dissolved oxygen and pH. Data loggers store the information until the lander is retrieved. Acoustic release mechanisms bring the landers safely back to the surface. The El Atalant scientific team analyzed the recovered data sets. They mapped the dispersion of hydrothermal plumes across the basin. Ocean currents transport the vent minerals over vast underwater distances. The geochemical footprint of the Mediterranean vents is surprisingly extensive. This research links local volcanic venting to regional ocean chemistry. Not all Mediterranean vent research requires heavy deep-sea equipment. The shallow vents near Panaria Island offer highly accessible study sites. These vents lie at depths between 10 and 30 meters. Scientific divers conduct direct observation and careful manual sampling. The National Research Council of Italy maintains a permanent base here. Divers install delicate flow meters directly over the bubbling fissures. They measure the exact volume of gas released into the water column. Carbon dioxide dominates the gas composition at the shallow Panaria sites. Scientists use these shallow volcanic vents as natural underwater laboratories. They study the effects of ocean acidification on local marine life. The continuous gas release lowers the pH of the surrounding water. Researchers monitor the calcification rates of nearby vulnerable coral species. This accessible site provides invaluable data for global climate change models. The Panaria research complements the deeper and more complex seamount expeditions. Modern expeditions rely heavily on international scientific collaboration. The Eurofleet's program facilitates shared access to specialized research vessels. Scientists from Spain, France, and Italy frequently form joint research teams. The Spanish research vessel Sarmiento de Gamboa participated in recent surveys. This modern ship features highly advanced dynamic positioning systems. Dynamic positioning allows the vessel to hover precisely over a vent. The crew deployed a gravity corer to sample the surrounding sediments. Sediment cores reveal the historical deposition of various hydrothermal minerals. Geologists slice the cores into thin sections for detailed microscopic analysis. They identify specific mineral grains ejected during past violent venting events. Radiocarbon dating of embedded microscopic shells provides a strict chronological framework. The collaborative approach significantly accelerates data processing and scientific publication. Shared databases allow researchers worldwide to access the newly discovered findings. Acoustic monitoring has revolutionized our understanding of vent fluid dynamics. Researchers deploy passive acoustic monitors near the active mineral chimneys. These hydrophones record the continuous sound of boiling and venting. The acoustic frequency correlates directly with the velocity of the fluid. Higher frequencies indicate extremely rapid and pressurized gas release. Lower frequencies suggest a steady and slow flow of hot liquid. Scientists use complex machine learning algorithms to process the audio data. The software identifies distinct acoustic patterns associated with specific geological events. In 2017, the acoustic network detected a sudden massive increase in activity. The fluid flow rate at the Marseille seamount doubled over 2 weeks. This surge coincided perfectly with a period of regional tectonic stress. Acoustic monitoring provides a non-invasive method for tracking overall vent health. The sensitive hydrophones require minimal power and operate continuously for years. Future expeditions will utilize even more advanced autonomous robotic systems. Engineers are developing resident underwater vehicles for the EMSO network. These rovers will live permanently on the dark Mediterranean seafloor. They will dock at the cabled observatories to recharge their batteries. Scientists will control the deep rovers from comfortable laboratories on land. The rovers will perform daily routine inspections of the hydrothermal vents. They will carry modular sensor payloads for highly specific scientific tasks. One payload might measure heavy metal concentrations in the surrounding sediment. Another might photograph the slow growth of microbial mats over time. This resident technology eliminates the pressing need for expensive surface ships. Continuous robotic presence will capture transient biological and unexpected geological events. The deep Mediterranean will soon become a fully wired scientific laboratory. Synthesizing data from multiple scientific disciplines presents a significant analytical challenge. Oceanographers must carefully merge chemical, biological, and geological research datasets. Supercomputers process the incredibly complex variables of the extreme hydrothermal environment. Three-dimensional models visualize the precise flow of fluids through the crust. These models incorporate thermal temperature gradients and solid rock porosity measurements. Scientists input the exact geographical coordinates of the Marseille and Palinuro vents. The digital simulations predict exactly how the vent systems will evolve. They show the gradual and steady cooling of the underlying magma chambers. The models also simulate the complex chemical reactions within the mineral chimneys. This computational approach guides the strategic planning of future physical expeditions. Researchers target specific seafloor locations predicted to yield highly anomalous data. The powerful synergy between field observation and computer modeling drives discovery. The human element of deep-sea research requires immense personal dedication. Scientists spend long weeks at sea in cramped and isolated conditions. They work in rotating 12-hour shifts to maximize continuous data collection. The hum of the ship engines provides a constant mechanical background noise. Monitors display endless streams of telemetry from the dark depths below. A successful ROV dive requires intense and unbroken concentration from the pilot. The chief scientist carefully directs the complex and delicate sampling procedures. Every single milliliter of vent fluid is precious and carefully catalogued. The safe recovery of an instrument lander brings a profound sense of relief. Global hydrothermal systems present fascinating geological contrasts across different oceanic ridges. The Mediterranean vents differ significantly from massive Pacific Ocean structures. Pacific Ring of Fire vents sit directly at active tectonic plate boundaries. The East Pacific Rise features towering black smoker mineral chimneys. Those Pacific structures emit heavily mineralized dark hydrothermal fluid plumes. Mediterranean systems reside within a slowly closing ancient ocean basin. These Tyrrhenian sea vents emit clear shimmering high-temperature fluids instead. Pacific vent temperatures frequently reach 400 degrees Celsius easily. Mediterranean fluid temperatures generally peak around 200 degrees Celsius. Geologists map these thermal variations across the global seafloor network. Each unique vent field reflects its specific local crustal rock composition. The Juan de Fuca Ridge hosts highly active volcanic vent systems. Scientists compare those Pacific ridges with Mediterranean submarine seamount chains. Deep subduction zones create distinct chemical signatures in the expelled fluids. Tectonic forces shape the fundamental architecture of these deep marine environments. The Mid-Atlantic Ridge hosts the famous Lost City hydrothermal field. Lost City relies entirely on slow serpentinization chemical rock reactions. Mediterranean vents also utilize similar ancient geochemical mineral transformation processes. The vast Indian Ocean contains the deep Kyre vent field. Kyre hydrothermal fluids contain unusually high dissolved hydrogen gas concentrations. Mediterranean fluids show distinct isotopic carbon and sulfur chemical signatures. Thick ancient evaporite layers cover the Mediterranean seafloor basalt crust. These massive subterranean salt layers influence the regional hydrothermal chemistry. Atlantic and Pacific vents completely lack this thick sedimentary salt blanket. The fluid mineral composition changes drastically based on geological differences. Researchers analyze fluid samples from the entire global ocean network. Isotope mass spectrometry reveals the deep origins of these fluids. The Mediterranean retains the chemical characteristics of a much older ocean. Tectonic isolation shapes this unique regional hydrothermal environment quite completely. Geological isolation creates a perfect natural laboratory for marine chemists. Deep marine ecosystems face unprecedented modern anthropogenic environmental destruction threats. Commercial industrial interests target hydrothermal mineral deposits across the globe. Polymetallic massive sulfides accumulate near these highly active vent chimneys. Mining companies actively seek concentrated copper, zinc, and rare gold. The International Seabed Authority regulates deep ocean floor extraction claims. Mediterranean nations negotiate specific regional environmental protection international legal frameworks. The Barcelona Convention addresses regional marine conservation policy implementation strategies. Commercial bottom trawling damages fragile mineral chimney structures almost permanently. Heavy industrial fishing gear leaves deep physical scars on ocean sediments. Suspended mud plumes choke delicate filter-feeding vent organisms very quickly. Physical destruction disrupts the complex local hydrothermal fluid flow dynamics. Broken mineral chimneys alter the crucial thermal gradients required for survival. Industrial acoustic noise pollution also disrupts sensitive benthic marine life. Commercial vessel traffic alters the natural acoustic environment significantly here. Seismic air guns create devastating pressure waves across the ocean floor. Marine biologists advocate strongly for strict deep ocean protected areas. The Palinuro seamount requires immediate international conservation legal protection status. Endemic biological species cannot survive sudden catastrophic habitat destruction events. Vent organisms exhibit extremely slow biological reproduction and growth rates. Ecosystem recovery from physical disturbance takes multiple long decades minimum. Conservationists propose extensive protective buffer zones around all active vents. Monitoring stations track subtle environmental changes continuously without any interruption. Advanced sensor networks record shifts in biodiversity and fluid chemistry. Genetic isolation makes Mediterranean vent populations particularly highly vulnerable targets. The tragic loss of a single chimney can eliminate entire colonies. Scientists deploy autonomous cameras to document these fragile deep habitats. Photogrammetry provides essential baseline data for future environmental impact assessments. International scientific cooperation remains essential for effective deep-sea preservation. Global treaties must balance scientific research with strict environmental protection. Preserving these ancient ecosystems ensures the survival of unknown species. These ancient deep vents offer vital clues about early biological evolution. Scientists examine the last universal common ancestor of all terrestrial life. This theoretical ancient organism likely thrived in extreme thermal environments. Hydrothermal mineral chimneys provide natural chemical gradients for early cellular metabolism. These precise chemical gradients generate essential cellular energy for biological survival. Alkaline vent fluids mix with acidic ocean water constantly and violently. This continuous fluid mixing creates natural electrical proton motive forces. Iron and sulfur compounds act as critical inorganic biological catalysts. Researchers simulate these exact extreme conditions in controlled laboratory settings. Geochemist Michael Russell proposed the alkaline hydrothermal vent origin hypothesis. His groundbreaking theory connects basic geochemistry directly to early biochemistry. Mediterranean vents serve as highly accessible ancient Earth geological analogues. Porous rock structures mimic primitive cellular lipid membrane physical formations. Mineral surfaces concentrate simple organic molecules highly effectively down here. Thermal energy drives the synthesis of complex organic chemical structures. Basic amino acids form naturally under extreme high hydrostatic pressure. The RNA world hypothesis requires stable thermal aquatic chemical environments. Deep vent crevices protect fragile genetic molecules from harsh cosmic radiation. Harmful ultraviolet solar light cannot penetrate these dark ocean depths. Deep chemosynthesis predates shallow solar photosynthesis by several billion long years. Microbes here utilize toxic hydrogen sulfide for daily metabolic energy. This specific metabolic pathway represents a truly ancient survival strategy. Thermophilic bacteria process inorganic chemicals into highly usable organic carbon. Astrobiologists study these marine systems for future robotic planetary exploration. Similar active hydrothermal vents might exist on Jupiter's icy moon Europa. Saturn's moon Enceladus shows clear evidence of subglacial hydrothermal activity. Silica nanoparticles found in deep space suggest active alien ocean vents. Understanding Mediterranean systems helps identify potential extraterrestrial biological chemical signatures. The fundamental chemistry of life follows universal thermodynamic physical laws. Water and geothermal heat create the perfect cradle for early life. Exploring these dark ocean depths requires advanced marine engineering solutions. The ambient water pressure exceeds 300 atmospheres down here. Cold salty seawater causes severe galvanic corrosion on exposed metal instruments. Hydrothermal vent fluids are highly acidic and chemically highly destructive. Engineers use thick titanium alloys for spherical equipment pressure housings. The famous research vessel Alvin pioneered early deep ocean physical exploration. Modern remotely operated vehicles utilize high-definition fiber optic data cables. The JSON ROV maps complex thermal vent fields with incredible precision. Synthetic syntactic foam provides essential physical buoyancy for these heavy machines. Electrical components require specialized pressure-compensated oil-filled protective enclosure systems. Glass instrument spheres must withstand immense uniform external crushing forces. Microscopic structural material flaws cause catastrophic implosions at these extreme depths. Scientists monitor equipment integrity through continuous acoustic telemetry data feedback. Every mechanical joint requires specialized deep-sea waterproof chemical lubrication compounds. Maintaining robotic equipment at sea demands constant rigorous mechanical troubleshooting. Autonomous underwater vehicles navigate complex uneven seafloor terrain completely independently. The advanced AUV Sentry operates entirely without a physical control tether. Battery technology limits autonomous survey mission durations quite significantly today. Lithium-ion power cells must withstand freezing ambient deep water temperatures. Acoustic communication suffers from severe wireless data bandwidth capacity limitations. Data transmission rates remain frustratingly slow through dense liquid water. Scientists rely on pre-programmed complex inertial navigation computer software algorithms. High-resolution sonar mapping requires precise acoustic transponder seabed tracking networks. Positioning calculation errors occur due to local water density variations. Steep thermal temperature gradients bend acoustic sound waves highly unpredictably. Robotic manipulator arms require delicate hydraulic force feedback sensor systems. Sampling fragile mineral chimneys demands extreme mechanical joystick control precision. Skilled pilots operate these complex machines from surface ship control rooms. Latency in live video transmission complicates delicate physical sampling procedures. Current technology pushes the absolute limits of modern ocean engineering. Deep hydrothermal systems concentrate highly valuable geological and chemical resources. Massive sulfide mineral deposits form slowly over many thousands of years. These unique geological structures contain high grades of rare industrial metals. Cobalt and tellurium precipitate directly from the hot expelled fluids. Modern technology manufacturing industries require these specific rare earth elements. Manganese crusts accumulate slowly on exposed volcanic basalt rock surfaces. Geologists estimate the total global volume of these deep mineral reserves. Drilled core samples reveal the complex stratigraphy of ancient vent deposits. Radioactive isotopic dating determines the precise age of these mineral formations. The Marseille seamount contains significant undiscovered hydrothermal mineral wealth potential. Commercial extraction technologies remain currently in the early experimental developmental stages. Heavy mining vehicles must operate on steep, unstable volcanic mountain slopes. Suspended sediment plumes from mining would travel vast oceanic distances quickly. Environmental impact studies evaluate these proposed extraction methodologies extremely rigorously. The true ecological cost of deep seabed mining remains completely unknown. Marine bioprospecting offers incredible alternative economic value from vent ecosystems. Extremophile bacteria produce unique, highly heat-resistant biological protein enzyme structures. The revolutionary polymerase chain reaction relies heavily on such thermal enzymes. Taq polymerase originally came from a similar extreme hot thermal environment. Pharmaceutical companies screen deep vent microbes for novel antibiotic chemical compounds. Marine bacteria develop unique chemical defense mechanisms against microbial competitors. These isolated biological compounds show promise against modern drug-resistant pathogens. Industrial manufacturing processes benefit from pressure-tolerant biological chemical catalysts significantly. Advanced biofuel production utilizes specific metabolic enzymes from deep-sea archaea strains. The marine genetic resources hold truly immense global scientific potential. Researchers catalog complex microbial DNA sequences from global ocean vent sites. The Mediterranean biological genetic database expands with each new scientific expedition. Sustainable biological sampling requires only minimal physical organic material collection. Culturing these extreme deep microbes in surface laboratories proves extremely difficult. Most vent microorganisms simply refuse to grow inside artificial glass petri dishes. High-pressure titanium bioreactors simulate the natural deep ocean environmental conditions. Scientists manipulate water temperature and chemistry to encourage microbial cell growth. Modern genomic sequencing bypasses the need for traditional laboratory biological cultivation. Metagenomics reveals the entire complex biological community structure from water samples. This computational data helps map complex deep-sea metabolic food networks. The Mediterranean hydrothermal vents influence global climate systems. These geological structures release significant thermal energy daily. Geothermal heat alters local water density near the seafloor. Warm vent fluids mix with the surrounding cold brine. This continuous mixing drives localized thermohaline circulation patterns. The Levantine Basin experiences subtle temperature shifts from vents. Deep water formation relies on these precise thermal gradients. Carbon sequestration occurs naturally within these ancient hydrothermal fields. Vent chimneys absorb dissolved carbon dioxide from the ocean. Chemical reactions convert free carbon into solid mineral structures. Calcium carbonate precipitates build massive formations along fault lines. These mineral deposits lock away atmospheric carbon for millennia. Basaltic rocks react with acidic fluids at high pressures. This process creates stable magnesium carbonate on the seafloor. Oceanographers measure these carbon fluxes using benthic lander modules. Dr. Elena Ivanova documented these sequestration rates in 2019. Her team recorded carbon absorption at 3,200 meters depth. The Palinuro seamount acts as a massive marine carbon sink. Mineralization here prevents greenhouse gases from reaching the surface. Silicate weathering at the vents provides long-term climate regulation. The deep ocean acts as a massive thermal buffer globally. Vent systems regulate the chemical balance of the surrounding seawater. Iron particles from the vents fertilize distant oceanic surface waters. This iron stimulates phytoplankton growth across the broader Mediterranean basin. These microscopic plants absorb additional carbon dioxide from the atmosphere. The biological pump transports this organic carbon to the seafloor. Marine snow constantly falls upon the dormant hydrothermal vent fields. Benthic organisms consume this sinking organic matter with great efficiency. Hydrothermal activity contributes vast amounts of heat to the ocean. The Marseille seamount releases thermal energy through porous volcanic rock. This localized heating creates upward currents in the water column. Nutrient-rich bottom waters rise slowly toward the sunlit photic zone. Surface plankton blooms depend entirely on this deep-sea nutrient supply. The entire Mediterranean food web benefits from this thermal upwelling. Thermal anomalies extend kilometers away from the active vent sites. Sensors detect temperature spikes of 0.5 degrees Celsius nearby. These slight physical changes influence the Mediterranean outflow water. Dense saline water eventually spills westward into the Atlantic Ocean. Vent-heated fluids alter the complex salinity profile of the basin. Global ocean conveyor belts rely heavily on these regional inputs. The Tyrrhenian Sea functions as a massive thermodynamic underwater engine. Heat transfer rates vary across different regional hydrothermal vent fields. Scientists map these thermal plumes using acoustic Doppler current profilers. The precise data reveals intricate layers of moving water masses. Hydrothermal heat prevents complete stagnation in the deepest oceanic trenches. Oxygen distribution improves alongside these vital vertical marine convection currents. Benthic organisms thrive due to this constant deep water renewal. The physical oceanography of this region remains highly dynamic today. Future research aims to decode remaining mysteries of the vents. The absolute biological limits of deep-sea extremophiles remain completely unknown. Microbes here survive extreme heavy metal concentrations without apparent harm. Geneticists study how these organisms repair damaged cellular DNA structures. The evolutionary divergence of Mediterranean vent species puzzles marine biologists. These isolated populations show unique genetic adaptations over geological time. Researchers question when these specific species first colonized the basin. The Messinian salinity crisis likely caused massive regional extinction events. Current vent fauna may represent relatively recent biological recolonization efforts. Geologists also debate the remaining active lifespan of these seamounts. Magma chamber depletion rates suggest an eventual complete hydrothermal shutdown. The exact volume of the subsea floor biosphere requires accurate quantification. Microbial life extends deep into the fractured oceanic crust below. Dr. Marco Taviani proposes extensive subterranean bacterial networks currently exist. Drilling projects attempt to sample pristine fluids beneath the sediment. Deep core samples reveal ancient layers of hydrothermal mineral deposits. Complex isotope analysis will determine the precise age of these formations. The chemical exchange between crust and ocean needs precise mathematical modeling. Predicting future volcanic eruptions along the island arc remains highly challenging. Seismic monitoring networks currently track faint micro-earthquakes in the region. Advancements in marine technology revolutionize deep-sea hydrothermal vent scientific exploration. Autonomous underwater vehicles map the rugged seafloor with unprecedented detail. These robotic drones navigate complex volcanic terrain completely independently. High-resolution multi-beam sonar reveals hidden chimney structures in absolute darkness. Environmental DNA sampling changes how scientists catalog rare marine life. Water samples capture genetic material shared by passing deep-sea organisms. This technique identifies species without requiring physical biological specimen collection. Long-term benthic observatories provide continuous data streams to the surface. Cabled networks supply reliable power to deep-sea cameras and sensors. In-situ mass spectrometers analyze vent fluid chemistry in real time. These specialized instruments detect trace elements like dissolved gold and silver. Laser Raman spectroscopy identifies mineral compositions without altering fragile samples. Miniaturized sensors withstand crushing pressures exceeding 300 atmospheric units. Fiber optic cables transmit terabytes of scientific data to research vessels. Artificial intelligence algorithms process raw acoustic data to find new vents. Machine learning models predict hydrothermal activity based on geological features. Soft robotics allow gentle physical interaction with fragile biological specimens. Silicone grippers collect delicate sea sponges without causing structural damage. Pressure-retaining sampling chambers bring deep microbes to the surface alive. These technological leaps constantly expand our understanding of the deep ocean. New battery technologies extend the operational time of robotic submersibles. Lithium-ion power banks withstand the freezing temperatures of the abyssal plain. High-definition cameras capture the subtle physical textures of bacterial mats. LED lighting systems illuminate the dark seafloor without generating excess heat. Researchers use photogrammetry to create three-dimensional models of vent chimneys. These digital twins allow scientists to study structures from safe laboratories. Virtual reality headsets provide highly immersive experiences of the deep sea. University students can navigate the Palaneuro vent fields from their classrooms. Several international expeditions plan to revisit the Mediterranean vents soon. The European Space Agency uses these deep sites as planetary analogues. Harsh conditions here mimic the subsurface oceans of distant icy moons. Europa and Enceladus might host very similar hydrothermal vent systems. Testing equipment in the Mediterranean prepares delicate instruments for space travel. The MEDSUV project coordinates multiple prestigious European marine research institutions. Scientists will deploy new acoustic sensor arrays across the Aeolian Arc. Dr. Laura Crispini leads geological seafloor mapping efforts for this initiative. Her dedicated team focuses on structural fault lines controlling fluid flow. Manned submersibles will dive to the unexplored flanks of Mount Vavilov. Researchers expect to find undiscovered species of rare chemosynthetic bacteria. Acoustic modems will establish wireless communication networks between seafloor nodes. These nodes will monitor tectonic plate movements with absolute millimeter precision. Geochemists plan to measure rare earth element concentrations in vent fluids. Biologists will conduct long-term colonization experiments on submerged artificial substrates. Sunken wood falls and bone deployment will attract highly specialized scavengers. Time-lapse cameras will record the slow development of new biological communities. Oceanographic vessels like the Urania provide essential logistical surface support. Multidisciplinary scientific teams analyze data across biological and geological boundaries. The next decade promises incredibly significant discoveries in this deep basin. The Mediterranean vents represent a living window into Earth's ancient history. These complex hydrothermal systems operated long before human civilization ever began. The tectonic legacy of the ancient Tessis Ocean persists quietly here. Massive continental collisions forged this complex and isolated deep marine basin. Life at these active vents demonstrates remarkable resilience against extreme odds. Organisms flourish in total absolute darkness under crushing hydrostatic water pressure. Toxic vent chemicals provide the foundation for a thriving biological oasis. The striking juxtaposition of extreme heat and freezing water creates boundaries. These sharp chemical gradients drive continuous biological innovation and genetic adaptation. The sheer geological age of these massive formations commands profound respect. Fragile chimney structures grow millimeter by millimeter over countless dark centuries. Solid mineral deposits record the shifting chemical composition of ancient oceans. Every scientific expedition reveals another hidden layer of this intricate ecosystem. The deeply interconnected nature of all marine life becomes apparent here. Microscopic chemosynthetic bacteria support large dense fields of specialized tube worms. Blind predatory crabs navigate the sharp mineral spires in search of food. The silent ballet of deep-sea biology continues completely uninterrupted by human time. These hidden marine worlds operate completely independent of any solar energy. Chemosynthesis proves life can conquer the most hostile physical environments imaginable. The quiet resilience of the deep ocean inspires scientific curiosity globally. Protecting these fragile hydrothermal deep-sea ecosystems remains an urgent global priority. Commercial deep-sea mining poses a significant threat to these pristine environments. Mining companies seek valuable heavy metals deposited within the vent chimneys. Extracting these precious minerals would destroy centuries of slow biological growth. Sediment plumes from mining operations could smother neighboring fragile benthic communities. The incredibly slow growth rates of deep-sea organisms severely hinder ecosystem recovery. Designated marine protected areas must encompass these active hydrothermal seafloor fields. International maritime treaties attempt to regulate resource extraction in international waters. The Mediterranean basin requires specific regional conservation agreements and strict enforcement. Marine scientists advocate for preserving the Marsilii and Palinuro seamounts entirely. Untouched deep wilderness holds immeasurable intrinsic ecological value for future generations. Unique genetic resources found here could revolutionize modern medicine and biotechnology. Enzymes from deep extremophiles already improve industrial manufacturing processes globally today. Destroying these rare habitats erases potential scientific medical breakthroughs forever. Marine conservation efforts rely heavily on public awareness of these hidden realms. Documenting the rich biodiversity of the vents highlights their crucial ecological importance. Strict environmental regulations must govern all scientific sampling and commercial exploration. Acoustic noise pollution from heavy maritime traffic also affects deep-sea fauna. Commercial vessel noise disrupts the vital communication of marine mammals and fish.